The universe is slowly fading to black. Our most advanced science points toward a final epoch of cosmic light, a time when the last stars will grow quiet and the cosmos will enter an age of deep stillness. This is not a fictional tale, but the ultimate destiny predicted by our understanding of physics. In this journey, you will gain a completely new perspective on reality, time, and our brief, brilliant moment within it. We will uncover the hidden forces behind this great transition and explore what the silent future of the cosmos says about existence itself. How does the knowledge of an ending change the way you see the night sky right now? That first dawn was not a gentle sunrise but a powerful, brilliant revolution. For hundreds of millions of years, the cosmos was a featureless, silent sea of darkness, a fog of simple gas. Then gravity began to pull, gathering the first pockets of hydrogen and helium. These clumps grew denser and hotter until, deep within them, a new kind of fire was born. Nuclear fusion ignited, and the very first stars blazed into existence, transforming the primordial gloom. These were not like the stars we see today. They were giants, hundreds of times more massive than our sun, living fast and concluding their lives in spectacular events that enriched the cosmos with the first complex elements. This was the cosmic dawn, the moment light became a permanent feature of reality. Today, we are witnessing this ancient dawn through the eyes of the James Webb Space Telescope. It peers back across unimaginable distances, its infrared vision capturing the faint, stretched light of those earliest galaxies. We see them not as they are, but as they were, their light only now reaching us after a journey of over 13 billion years. Each faint smudge is a testament to that initial, glorious burst of creation. To understand the closing of all light, we must first appreciate this profound beginning. The universe emerged from darkness once. That transformation set the stage for everything that followed, from the formation of our own sun to the evolution of life itself. It was the opening act in a grand cosmic story of illumination, a story whose final chapters are written not in light, but in shadow. That brilliant dawn of starlight was only possible because the universe was a smaller, more intimate place. But a fundamental shift has occurred, a change so profound it rewrote the cosmic destiny. In the late 1990s, astronomers made a remarkable discovery. By observing distant stellar explosions, they found that the universe is not just expanding, it is accelerating. Something is actively pushing everything apart, and we call that something dark energy. This is not a substance you can touch or see. It is a property of empty space itself, a latent energy inherent to the vacuum that generates a kind of repulsive gravity. Think of the universe as a vast, stretching canvas. Dark energy isn't painting on that canvas, it is actively pulling at its edges, making the canvas itself grow larger and larger, faster and faster. This force now dominates the cosmos, accounting for roughly 70% of all the energy in existence. Its effect on light is just as profound. As galaxies are carried away from each other on this stretching fabric, the light traveling between them gets stretched too. Its wavelength lengthens, shifting toward the red end of the spectrum and slowly sapping its energy. The steady push of dark energy ensures that cosmic distances will eventually become vast beyond measure. It is the quiet engine guiding the universe toward a state of profound separation, where one island of stars will no longer see the glow of any other. This stretching of space itself has a direct and profound effect on the light traveling through it. As a light wave journeys across the expanding cosmos, the very fabric it moves through is being pulled taut, and the wave is stretched along with it. This lengthening of its wavelength shifts the light toward the red end of the spectrum, a phenomenon known as cosmological redshift. It is not that the galaxy itself is red, but that its light has been fundamentally changed by its long voyage. A simple analogy is to think of a wave drawn on a rubber band. As you stretch the rubber band, the crests and troughs of that wave are pulled farther apart. The wave itself becomes longer just as light becomes redder. This is not merely a curious observation. It is a direct message from the universe written in the very color of starlight. Astronomers use this redshift as a cosmic measuring tape. By carefully analyzing how much the light from a distant galaxy has been stretched, they can determine not only its distance but also its velocity away from us. The greater the redshift, the faster the galaxy is receding, carried away by the ongoing expansion of space. This observation provides the most compelling evidence we have for our expanding universe, a universe that was once far more compact and connected. Every redshift measurement is a glimpse back in time, revealing the universe's expansion history encoded in ancient light. Yet this same process that allows us to peer into the past also shapes a distant future. As the expansion continues, the light from far-off galaxies will be stretched so far that its wavelength will shift beyond red, into the infrared, and then even further, until it becomes undetectable to any instrument we might imagine. The light will still be traveling, but its message will have been stretched beyond recognition, a direct consequence of the stretching fabric of reality. This stretching of light leads us to a profound and inescapable truth. There is a fundamental boundary to what we can ever see, a cosmic horizon defined by the speed of light and the relentless expansion of space. We call this the Hubble volume, and it defines our entire observable universe. Picture a vast, shimmering bubble centered from our perspective, right here on Earth. Everything we can see, from the moon in our sky to the most distant galaxy, exists inside this sphere. Its edge is not a physical wall, but a frontier in time. It marks the point where the expansion of space carries galaxies away from us so quickly that their light can no longer make progress against the stretching void between us. The light they emit today is destined to travel forever without ever arriving. Our bubble is not static. It is constantly changing as new light, emitted billions of years ago from galaxies even farther away, finally completes its long journey to our telescopes. We are always receiving new yet ancient messages. However, this expansion also sets a firm limit. The Hubble volume is the largest this bubble of visibility can ever become. As cosmic acceleration continues, the fate of galaxies at the very edge of our view is sealed. They will not merely grow dim, they will, from our perspective, fade from sight. The space between us will stretch faster than light can traverse it, effectively removing them from our future sky. This is not because the galaxies themselves are being lost, but because the information of their existence can no longer reach us. The universe is slowly drawing a veil across the cosmos. This gradual separation, where our observable bubble effectively grows more distant over eons, is the first quiet step toward the great fading of light. Yet even as the grand cosmic horizon recedes, pockets of fierce resistance remain. On the largest scales, dark energy is the undisputed ruler, but within the crowded neighborhoods of galactic clusters, gravity still holds sway. Here, in these dense archipelagos of stars, the inward pull of matter creates a local counterforce to the global expansion. Picture two dancers locked in a powerful, spinning embrace. The music of the entire ballroom might be telling everyone to drift apart, but their own shared momentum and connection keep them tightly bound. This is the dynamic tension that defines our own cosmic home, the local group. Our Milky Way, the Great Andromeda Galaxy, and dozens of smaller satellite galaxies are all gravitationally tethered, forming a single, isolated family adrift in the expanding void. For now, the push of dark energy is insignificant here. The gravitational bonds are simply too strong. This local victory for gravity ensures a dramatic future for our own galaxy. In a cosmic dance set to unfold over billions of years, the Milky Way and Andromeda are destined to merge. They are not on a collision course in the way two objects might meet, but rather they are spiraling toward a final, magnificent union. Their stars are so widely spaced that direct stellar encounters will be incredibly rare. Instead, their mutual gravity will warp and reshape them, eventually weaving their stars and gas into a single, vast, ellipsoidal galaxy, a lasting testament to an ancient cosmic process. For a time, such galactic clusters will persist as brilliant islands of light, their internal structures holding firm against the stretching darkness outside. But this is a temporary reprieve. The relentless acceleration driven by dark energy is a constant cumulative force. Over trillions of years, even the powerful gravitational glue binding these clusters together will be tested and ultimately overcome. The space between individual galaxies within a cluster will itself begin to stretch, thinning out their connections until the cluster itself dissipates, its member galaxies drifting apart into the ever-widening emptiness. This is the distant future we are only beginning to comprehend, a time when every structure, no matter how grand, will face its final transition into the quiet, expanding night. The most immediate consequence of this cosmic expansion is already unfolding, a silent recession we can observe from our own vantage point. Galaxies far beyond our local cluster are not merely moving away, their light is undergoing a profound transformation. As the space between us stretches, the light from these distant island universes is redshifted, its waves pulled longer and longer. For now, our most powerful telescopes, like the James Webb, can still detect this light by observing in the infrared part of the spectrum, seeing the stretched starlight that our eyes cannot. But this is a temporary window. The acceleration of the universe ensures that for every galaxy beyond a certain critical distance, a point of no return awaits. Their light will eventually be stretched past the infrared, shifting into the realm of radio waves and then further still, into wavelengths so long and energy so low that they become undetectable to any conceivable technology. It is not that the galaxies themselves blink out of existence, but that the signal of their presence is stretched into silence, like a distant voice fading into a quiet, featureless hum. The cosmos will slowly seem to empty from the outside in. The grand tapestry of the night sky, filled with countless points of light, will begin to change. One by one, the most distant galaxies will fade from our records, their light having stretched beyond our ability to perceive. This is the first great dimming, a transition from a universe filled with visible neighbors to one that appears far more isolated. Our observable bubble will not burst, but it will steadily contract in terms of meaningful, detectable light. The brilliant backdrop of the cosmos will grow quiet, leaving our local galactic family seemingly alone in a vast and darkening ocean. This silent recession marks the initial phase of the Great Disappearance, a process that reshapes our fundamental view of reality from a vast, interconnected web to a much more localized and intimate portrait. This brilliant age of starlight rests upon a finite supply of cosmic fuel. Every star that ignites, from the smallest red dwarf to the most brilliant blue giant, is born from the collapse of immense clouds of interstellar gas and dust. This reservoir of raw material is not infinite. Over timescales that dwarf human history, the very process of star formation is what will ultimately bring it to an end. Galaxies are not static paintings, they are dynamic engines of creation and change. A young spiral galaxy, like our own Milky Way, is a vibrant stellar nursery. Its swirling arms are dense with molecular clouds, cold, dark regions where gravity can slowly work its magic, pulling gas together until the pressures and temperatures at the core become so immense that nuclear fusion sparks to life. A new star is born, but this cycle of birth consumes the very resources that make it possible. With each generation of stars, the galaxy's reservoir of available gas diminishes. Some of this material is locked away for billions of years within the long-lived stars themselves. A significant portion, however, is returned to space in dramatic events. When massive stars complete their life cycles in spectacular supernova explosions, they send newly forged heavy elements outward, scattering gas and dust and preventing it from immediately collapsing into new stars. In the most active galactic cores, supermassive black holes can unleash tremendous energies, their jets and radiation heating vast regions of gas and effectively quieting star formation across entire galaxies. Over eons, these processes transform a galaxy's character. A blue, star-forming spiral, rich with gas and youthful energy, gradually evolves. Its spiral arms fade as the gas is consumed or returned to the void. It settles into a quieter, more stable state, becoming what astronomers call an elliptical galaxy. These galaxies are often depicted as red and quiescent, their populations dominated by older, longer-lived stars with little to no ongoing star birth. The transition from a spiral to an elliptical marks a fundamental shift from a galaxy of creation to one of endurance. This is the future awaiting all galaxies. One by one, the stellar nurseries will grow quiet. The last pockets of cold, dense gas will either form the final generation of stars or be scattered by the last great releases of stellar energy. After this point, no new stars will ever ignite. The universe will no longer be a place of birth, but one of prolonged and gradual change. Its future illumination will depend entirely on the aging embers of the stars already shining, a cosmic legacy of light slowly burning down to its last fading glow. The final generation of stars will eventually exhaust the last of the galactic fuel, leaving behind a cosmos populated not by brilliant suns, but by their cooling embers. This marks the beginning of an epoch so long it defies human comprehension, the era of degenerate stars. The primary actors on this stage are white dwarfs, the Earth-sized cores of stars like our Sun. When a typical star exhausts its nuclear fuel, it sheds its outer layers, leaving behind an intensely hot core of degenerate matter. This exotic state is not held up by the heat of fusion, but by a quantum mechanical effect, a fundamental resistance to being squeezed any further. A single teaspoon of this material would weigh many tons on Earth. These newborn white dwarfs blaze with the residual warmth of their former lives, glowing at temperatures rivaling the surface of our Sun. But with no internal energy source, they are destined for an epic and irreversible cool down. Over trillions upon trillions of years, these stellar remnants will radiate their remaining heat into the ever colder void, slowly fading from white to yellow to a dim, deep red. The theoretical endpoint of this process is a black dwarf, a cold, dark sphere of pure carbon and oxygen, the same fundamental materials that make up a diamond. It would be a perfect crystal, a monument to a star that once was, drifting in absolute darkness at a temperature barely above the freezing void of space itself. Our universe is not yet old enough for a single black dwarf to have formed, making them ghostly inhabitants of a future we can only predict. They will be joined by other stellar remnants, like the incredibly dense neutron stars, which will also slowly cool and fade over similar cosmic timescales. In this twilight landscape, the very rhythm of existence changes. On any lone, frozen world still orbiting a black dwarf, the concept of day and night becomes meaningless. The sky would be perpetually, utterly black, punctuated only by the faint, cold light of other degenerate remnants, themselves mere fading embers in an unimaginably vast and empty theater. This is the long, quiet twilight of the cosmos, a period of slow fading that sets the stage for a far more profound and active darkness yet to come. Yet even these dark, crystalline remnants are not the final word. On timescales that make the fading of stars seem like a brief moment, the very foundations of matter may prove to be unstable. Enter one of the most profound and speculative ideas in all of physics, the concept of proton decay. We are taught that a proton is a stable, permanent fixture of the universe, an unchanging building block at the heart of every atom. But some of our most ambitious theories, known as grand unified theories, suggest this stability is only an illusion of our brief timescale. They predict that a proton can, in fact, spontaneously transform, decaying into lighter particles in an event of unimaginable rarity. The proposed half-life for this process is staggering, on the order of 10 to the 34 years or more. To grasp that scale, consider that the entire current age of our universe is only about 10 to the 10 years. You would need to watch a number of protons equal to all the matter in a billion galaxies for a time longer than the universe has existed just to have a reasonable chance of witnessing a single decay. This is not a process for any age of stars or galaxies, but for an epoch of deep cosmic darkness. The implications, should this idea be true, are absolute. Every complex structure left behind from the age of light would ultimately be erased. A black dwarf, that perfect diamond sphere, would not last forever. Its constituent protons would, one by one over these vast eons, wink out of existence. Each transformation would release a tiny burst of energy, slowly converting the mass of the ancient star into a faint spray of subatomic particles and radiation. The same fate would meet any wandering planets, asteroids, or even the diffused dust that once filled galactic space. All of it would gradually dissolve, not in fire, but in a slow, inexorable whisper of particle physics. The last structural footprints of the cosmic dawn, the very atoms forged in those first brilliant stars, would be systematically taken apart. What would remain is a universe growing ever more diffuse, a thin, cooling sea of leptons like electrons and positrons, and photons of ever-decreasing energy. It is a future that moves beyond mere darkness into a fundamental unraveling of the material world itself, leaving no lasting monument or memory of the galaxies and stars that once were. Even the most formidable structures in the cosmos are not immune to the slow march of time. Black holes, those ultimate symbols of gravitational might, were once thought to be permanent and indestructible sinks of matter and energy. But a revolutionary idea from Stephen Hawking revealed a startling truth. These cosmic giants are not eternal. They too will eventually fade, releasing their substance back into the universe through a process known as Hawking radiation. This phenomenon hinges on a strange quantum quirk occurring right at the edge of reality, the event horizon. According to quantum theory, empty space is not truly empty. It is a seething, bubbling foam of virtual particles, pairs of matter and antimatter that spontaneously pop into existence and then almost instantly annihilate each other. Normally, this dance happens too quickly to have any effect, but at the precipice of a black hole, the immense gravity can pull these particle pairs apart before they can reunite. One particle falls across the event horizon, vanishing forever into the black hole, while its partner escapes into space. To an outside observer, it appears as if the black hole has just emitted a particle. There is a profound cost for this escape. The energy for creating the pair and for propelling one particle away is drawn from the black hole's own gravitational field. In this exchange, the black hole loses a tiny, almost immeasurable amount of mass. This is Hawking radiation, a faint whisper of heat emanating from the coldest places in the universe. The rate of this evaporation is inversely related to the black hole's size. A small, stellar mass black hole would radiate more intensely and vanish in a comparatively brief time, perhaps over billions upon billions of years. But for the supermassive black holes that anchor galaxies, the timescales are almost beyond comprehension. A black hole with the mass of our Sun might take 10 to the 67 years to evaporate. For a giant with the mass of a large galaxy, the process could require a googol of years, that is a 1 followed by 100 zeros. This final conversion of matter into a diffuse, cooling radiation represents one of the last active processes in the entire cosmos. Long after the last star has faded to a cold, dark ember, the black holes will still be there, serving as the universe's final engines, slowly transforming the last remnants of structure into a formless, ever-expanding sea of particles and light. Their eventual departure marks the closing of a final chapter, the last act in a cosmic story that began with a brilliant dawn of light. Even the faintest whisper of heat from an evaporating black hole is a form of radiation, a ripple of light in the vastness. But this light, like all light, is subject to a final, quiet thief, the relentless expansion of space itself. This process is known as photon dilution. Picture a single drop of ink in a tiny glass of water, creating a deep, rich color. Now imagine that same drop of ink released into the ocean. Its color would become so faint, so spread out, that it would be utterly undetectable. This is the fate of every photon in the cosmos. As the fabric of space stretches, the light waves traveling through it are not only shifted to lower energies, they are also spread ever more thinly across an ever-increasing volume. The energy density of the universe, the amount of energy contained in any given cubic light year, is falling towards zero. The most profound example of this is the cosmic microwave background, the remnant glow from the Big Bang that still permeates all of space. Today, this afterglow has a temperature of about 2.7 degrees above absolute zero, a faint but measurable warmth that tells the story of our universe's fiery birth. But this temperature is not constant. It is tied directly to the expansion. As the universe grows larger, the wavelengths of these primordial photons are stretched, and their effective temperature drops. In a future stretching trillions of years from now, this background warmth will have faded to a fraction of a degree above absolute zero. Given enough time, it will approach that ultimate cold asymptotically, getting infinitely close to absolute zero, but never quite reaching it in any finite time. The universe is not only growing dark, it is becoming profoundly, irreversibly cool. In this distant epoch, particles and photons will become so isolated that a single electron might travel for distances longer than our current observable universe without ever encountering another particle. The cosmos will enter a state of near-perfect equilibrium, a silent, motionless sea where change is measured not in years, but in timescales that dwarf the entire previous history of the universe. This is the final state of maximum entropy, a universe so vast and dilute that the very concept of an event becomes a statistical impossibility, a cosmic quiet so deep it echoes with the memory of everything that once was. This grand, quiet fade leads us to the ultimate destiny predicted by our physical laws, a state scientists call the universal heat equilibrium. From a thermodynamic perspective, this is the final, unchangeable balance. The entire cosmos achieves a state of maximum entropy. You can think of entropy as a measure of evenness, a more precise way to see it as the final, smooth distribution of all energy. Picture a cup of hot coffee sitting in a room. The warmth from the coffee naturally flows out, gently heating the surrounding air until both the coffee and the air reach the same temperature. At that point, the energy has been perfectly spread out. No more work can be done. You cannot use that lukewarm air to power an engine. The universal equilibrium is this principle applied to the entire cosmos. All the vast energy released in the great beginning, all the brilliant light of countless stars, all the residual warmth from fading stellar remnants will have been gently dispersed across an immeasurably vast and ever-expanding space. The temperature everywhere will be the same, unthinkably close to absolute stillness, the point where all molecular motion settles into quiet. In this final state, no energy differences remain. There are no warm spots or cool spots, no variations in pressure or density that could ever drive a process again. The universe becomes a uniform, incredibly thin sea of fundamental particles and redshifted light, all existing in a profound and unbroken calm. This is not an explosive conclusion, but a quiet one. It is the end of all activity, the end of change itself. No new stars will ever form, no planets will orbit, no chemical reactions will occur. The great cosmic story, which began in a blaze of light and transformation, will have reached its final, lasting state. From this condition of perfect balance, the universe cannot return. It represents the absolute finality of the timeline we have been tracing, a quiet so deep it echoes for eternity. But the silent fade of heat death is not the only possible finale written into the laws of physics. A far more dramatic and abrupt conclusion awaits in one theoretical model, known as the Big Rip. This scenario hinges on a specific and thought-provoking property of dark energy. What if its repulsive force is not constant, but grows stronger over time? In this model, dark energy transforms into something scientists call phantom energy, a force that would not just push galaxies apart, but would actively accelerate its own influence on the cosmos. The stretching of space would not merely continue, it would run away with itself, becoming exponentially more powerful with every passing moment. The initial stages would mirror what we already see, with distant galaxies vanishing beyond our cosmic horizon. But then, the phantom energy would begin to win battles it currently loses. The gravitational bonds holding our local group of galaxies together would be the next to change. Billions of years before the rip itself, the Milky Way and Andromeda would be gently pulled apart, their grand merger interrupted by the overwhelming pressure of the vacuum itself. The very fabric of space between them would stretch faster than their mutual gravity could compensate for, separating our local family. This relentless acceleration would then turn inward, targeting individual galaxies. The phantom force would overcome the gravity binding stars together, pulling solar systems away from each other and dispersing them into the ever-widening void. The final acts would be swift and absolute. In the last moments before the rip, the force would reach down to a planetary scale, overwhelming the gravity that holds a world together. A planet like Earth would be calmly and systematically separated, its material scattered. Then, the energy would target the forces that bind matter itself. The same electromagnetic force that holds your molecules together would be overcome. In a fleeting, final instant, every atom, every atomic nucleus, and every fundamental particle would be gently pulled away from every other, isolated forever across an infinite and ever-expanding gulf. The timeline for such an event is profoundly distant, but it is finite. Rather than a near-infinite twilight lasting trillions of years, the Big Rip presents a definitive conclusion to all structure in a far shorter, though still unimaginable, time frame. This cosmic possibility serves as a powerful reminder that our vision of the far future is painted with theoretical brushes, and the ultimate fate of all we see remains one of the greatest open questions in science. Yet within this seeming finality, a whisper of potential remains. The same quantum laws that govern the subatomic world suggest that a perfect vacuum is never truly empty or still. Even in the deepest cold of the universal heat equilibrium, tiny spontaneous shifts would continue to occur. These are not fluctuations of heat or light, but of the very fabric of spacetime itself. Energy can briefly and randomly emerge from apparent nothingness, creating ephemeral particles that vanish almost as quickly as they form. In our current universe, these events are microscopic and fleeting. But in a cosmos that is essentially eternal and infinite in its future extent, the improbable is not impossible. Given an endless amount of time, a quantum shift of any size, no matter how unlikely, could eventually happen. Imagine the silent, empty universe not as a static painting, but as a calm, dark ocean. On the surface, nothing seems to move, but deep below, a single, colossal bubble might spontaneously form. This is the speculative but staggering idea of cosmic renewal. A quantum shift on a grand enough scale could trigger a localized expansion of spacetime, a new beginning emerging from the absolute silence. From our perspective, it would be an event happening in a void so distant and disconnected we could never observe it. But from within that new bubble, an entire cosmos would awaken, filled with new energy, new particles, and a new story of light and structure beginning all over again. This concept, known as eternal inflation, paints a picture of a multiverse in a constant state of creation, where our entire universe is but one bubble in a vast, timeless froth of cosmic rebirth. It offers a profound counterpoint to the narrative of absolute finality, suggesting that even in the deepest silence, the potential for a new dawn is never entirely gone. Stand on a world orbiting one of the last ancient stars, trillions of years from now. An astronomer peers into their telescope, but the grand tapestry we see is gone. Their entire universe is the single, merged galaxy they call home, a silent island of faint, red dwarfs and cooling stellar embers drifting in an ocean of absolute black. Every external galaxy has long since been carried beyond the edge of visibility by the stretching of space, their light stretched into a formless, undetectable whisper. The concept of an expanding universe so fundamental to our understanding would be completely unknowable to them. With no receding galaxies to observe, no redshift to measure, the central pillar of modern cosmology simply would not exist. Their entire cosmic context would be this one solitary structure, and they would naturally assume it was the entirety of existence. The very notion of a cosmic beginning, a Big Bang, would be an inaccessible secret. The key evidence, the cosmic microwave background radiation, would have redshifted so far that its wavelength would be larger than the observable universe itself. That faint afterglow, our most direct window into the universe's earliest moments, would have faded into complete undetectability, taking the story of cosmic origins with it. How would physics develop in such isolation? Their science would be built upon the laws governing their immediate environment, the slow dance of degenerate stars, and the peculiar physics of extreme cold and near vacuum. They might never conceive of dark energy or an initial fiery state, their theories inevitably pointing toward a static, eternal, and lonely cosmos. This future intelligence, no matter how advanced, would be living in the quiet echo of a universe, surrounded by the legacy of a glorious past they could never know we were privileged to see. This knowledge of a final cosmic quiet does more than expand our understanding of physics. It reaches into the very core of our human experience. We are the universe becoming aware of itself, and in that awareness we are confronted with a profound paradox. Our cultures, our art, and our deepest personal yearnings often speak of eternity, of legacies that endure forever. Yet the cosmos itself, the ultimate stage for all existence, carries an expiration date written into its fundamental laws. This is not a failure, but a fundamental characteristic of reality. The universe is not a static monument, it is a dynamic and unfolding story, and every story has a final chapter. The fact that our chapter is one of light and life, however brief, is what makes it so phenomenally precious. The predicted end does not erase our significance, it redefines it. It shifts the foundation of meaning from an impossible quest for permanence to a profound appreciation for the transient moment we inhabit. We are not just bystanders in a cosmic drama, we are active participants in its most vibrant and brilliant act. The very atoms that form our bodies were forged in the hearts of ancient stars, and the consciousness we use to ponder the cosmos is a rare and beautiful product of this specific era of light. This realization can inspire a powerful form of cosmic gratitude. We are here against staggering odds during the cosmic day. We get to witness the grandeur of galaxies, feel the warmth of a star, and experience the richness of a living world. In the face of an eventual, silent future, the present becomes infinitely more valuable. The inevitable fading of all things on this scale can be seen not as a tragedy, but as the very thing that gives our fleeting moment its unique and poignant beauty. The quiet to come does not diminish the light we have now. It makes its brilliant, temporary shine all the more worthy of our wonder and our care. To uncover the fate of the cosmos, we must first learn to read its diary, written in the language of ancient light. Our current era, a brilliant sliver of cosmic time, provides the only clues we will ever have to forecast a future of deep stillness. The primary tool for this detective work is the detailed mapping of the universe's large-scale structure. By charting the positions and motions of millions of galaxies, cosmologists can trace the subtle fingerprints of dark energy's influence across billions of years. This is not a single snapshot, but a cosmic flipbook, allowing us to watch the expansion of the universe unfold and accelerate over time. How do we build such a map? Projects like the Dark Energy Survey have spent years scanning vast portions of the sky, using incredibly sensitive digital cameras on large telescopes to capture the light from distant galaxies. Each galaxy's position and its redshift, that stretching of its light we discussed, gives us two crucial data points: its location in three-dimensional space and its velocity away from us. When you plot millions of these points, a breathtaking pattern emerges, a cosmic web of filaments and voids, the largest structure we know of in existence. This web is the preserved record of gravity's initial pull and dark energy's subsequent push. By measuring the precise geometry of this web at different cosmic epochs, scientists can measure the strength of dark energy throughout the universe's history. The upcoming Euclid spacecraft, a mission led by the European Space Agency, is designed to take this mapping to a whole new level of precision. From its vantage point in space, free from the distortion of our atmosphere, Euclid will create a three-dimensional map covering nearly one-third of the entire sky, charting billions of galaxies stretching back over 10 billion years. This monumental data set will allow us to test whether dark energy has remained constant, as in the heat-death scenario, or if it has been changing, potentially pointing toward a more dramatic finale like the Big Rip. We are, in effect, using the present-day universe as a vast archaeological site, carefully sifting through the light of ancient stars to read the opening lines of a story whose final, quiet paragraphs are shaped by the fundamental constants of physics themselves. Our own galaxy's future offers a tangible starting point for this epic timeline. In roughly 4 billion years, the Milky Way and Andromeda will begin their majestic collision, a slow dance that will ultimately weave them into a single, larger galaxy often called Milkomeda. This event, dramatic as it is, occurs in what is essentially the immediate future on our cosmic scale, a mere blink in the eye of the universe. For trillions of years after this merger, the new galaxy will continue to shine, though its character will steadily change. Around 10 trillion years from now, the last reserves of interstellar gas will be exhausted, and the final star will be born. The era of star formation, the cosmic day that began with the first brilliant giants, will have drawn to a permanent close. From this point forward, the universe is living on borrowed light, its brilliance slowly dimming as its stellar population ages. To grasp these durations, we must shift our perspective entirely. The entire history of our universe from the Big Bang to today spans about 13.8 billion years. Now, extend that timeline outward not by doubling or tripling it, but by orders of magnitude. The end of star formation happens at 10 to the 13 years. The fading of the last small red dwarf stars occurs around 10 to the 14 years. We are now speaking in timescales that are 1,000 times longer than the current age of the cosmos. This is the beginning of the degenerate era, where the dominant objects are the cooling remnants of stars, the white dwarfs and neutron stars we discussed. Their slow fade into black dwarfs is an epoch in itself, a process that will take an almost incomprehensible 10 to the 15 years, or 100,000 times the current age of the universe. And still, this is only the middle of the story. The final transformation of matter through proton decay, should it occur, unfolds over a staggering 10 to the 34 years or more. How can we possibly visualize such a number? If you were to count every single grain of sand on every beach and in every desert on Earth, you would not even come close to this figure. It is a number that exists in the realm of pure mathematics, a testament to the patience of cosmic processes. The evaporation of the largest black holes marks one of the final chapters, a process requiring a googol of years, a 1 followed by 100 zeros. This is not merely a long time, it is a duration so vast that the entire previous history of stars and galaxies becomes an infinitesimally brief prologue. Our present moment, this era of brilliant galaxies and vibrant stellar life, is known to cosmologists as the stelliferous era, the age of stars. We do not live at the beginning or the end of this age, but at its very peak, a period often called cosmic noon. It is a fleeting, spectacularly bright moment nestled between a long, dark infancy and an immeasurably longer, darker future. Recognizing our place in this timeline transforms our relationship with the night sky. The stars we see are not permanent fixtures. They are a temporary, radiant bloom in a cosmos that is destined for quiet, making the light we are privileged to witness now all the more extraordinary. Our current vision of a fading cosmos rests on a foundation of profound, and perhaps fragile, certainties. The entire timeline we have traced, from the last starlight to the final transition of black holes, is built upon our understanding of physical laws as they operate today. Yet we must ask a deeply humbling question. Can we truly be sure these laws will remain unchanged over trillions upon trillions of years? The very constancy of nature's constants is one of our greatest assumptions. We take for granted the strength of gravity, the speed of light, and the behavior of dark energy as fixed features of reality. But what if they are not? Some ideas in particle physics suggest the fundamental forces we observe might be the result of a specific and potentially temporary state of our universe. A subtle shift in one of these constants, even over an immense timescale, could rewrite the entire cosmic endgame. The quiet fade we predict could be interrupted by a process we have not yet even imagined. This is not a failure of science, but its very essence. Our models are the best possible maps we can draw with the data available to us right now. They are not the territory itself. Every new discovery, from the accelerating expansion to the detailed structure of the cosmic microwave background, has forced us to redraw our maps. The next great discovery could be just around the corner, waiting in the data from an observatory like Euclid or the James Webb Telescope, ready to reveal a twist in the plot that changes everything we think we know about the final fate of all things. The greatest unknown in this entire narrative is the true nature of dark energy. Our standard model treats it as a cosmological constant, an unchanging force inherent to the vacuum of space. This simple assumption leads directly to the long, slow transition we have described. But what if dark energy is not constant? What if it is a dynamic field, one that can weaken or strengthen over time? If it were to weaken, the acceleration of the universe could slow, potentially allowing gravity to regain a foothold on the largest scales over an immense duration. A far more dramatic possibility is that it could strengthen, evolving into the phantom energy that triggers a big rip. Our current observations provide a snapshot, a single frame from a movie that is billions of years long. We are trying to extrapolate the entire plot from that one image. We simply do not have enough data to rule out these alternative futures. The mission of modern cosmology is to collect more frames, to measure the expansion history with such precision that we can finally discern whether the push of dark energy has always been the same, or if it holds a secret capacity for change that will redefine the ultimate destiny of the cosmos. This inherent uncertainty is not a reason for despair, but a celebration of the scientific journey. It reminds us that our quest to understand the universe is a story of continuous revision and deepening wonder. The cosmos is under no obligation to conform to our current theories. Every time we build a model that seems to explain everything, the universe has a way of presenting a new mystery, a fresh anomaly that challenges our complacency. The predicted fade to black is the most logical conclusion based on everything we currently know, yet it is painted with the brush of today's knowledge. The true final chapter of the universe remains one of the greatest open questions in all of human thought, a mystery whose solution may require not just more data, but a fundamental revolution in our understanding of physics itself. Our map of the cosmic end is detailed and compelling, but the vast, silent territories of deep time that lie ahead are sure to hold surprises we cannot yet conceive. Our quest to understand the cosmos may be the most meaningful legacy we leave upon the stage of time. We are a species that can look up at the silent stars and not only wonder, but actually decipher their story. We have traced the narrative from a brilliant beginning to a quiet, distant future, assembling this epic from faint whispers of light and the subtle mathematics of physics. This act of comprehension is a profound event in itself, a flash of conscious awareness in the long, dark night of the cosmos. Our scientific endeavors, from building great telescopes to formulating theories of spacetime, create a kind of memory for a universe that will one day forget its own luminous history. We are giving voice to the story of existence. The value of this quest is not diminished by the eventual fading of the stars, it is defined by it. In a cosmos destined for silence, our brief, brilliant moment of asking questions and seeking answers becomes a singular and precious event. It is our way of bearing witness, of adding a chapter of understanding to the grand cosmic story before the final pages turn. This legacy of curiosity is our unique gift to the universe, a testament that for a fleeting time there was not just light, but a mind to perceive it and a spirit to marvel at its passing. The silent fate awaiting the cosmos is written into the relationship between light and time itself. At the heart of this connection lies a profound truth revealed by Einstein, that space and time are not separate stages but a single, interwoven fabric called spacetime. The speed of light is not merely a cosmic speed limit. It is a fundamental constant that defines the very geometry of this fabric, dictating the flow of cause and effect across the universe. Imagine spacetime as a vast, still pond. An event, like a pebble dropped into the water, creates ripples that expand outward at a fixed speed. These ripples represent the fastest any information or influence can travel, the speed of light. For any observer on that pond, an event only becomes part of their reality, part of their now, when its ripples finally reach them. This creates what physicists call a light cone, a map of all points in spacetime that can possibly be connected by a signal traveling at or below the speed of light. Your personal light cone defines your entire observable universe, everything you can possibly know, interact with, or be influenced by. It is the ultimate boundary of your causal reality. In a static universe, these light cones would eventually encompass everything, weaving a single, shared cosmic history. But our universe is not static, it is stretching. The accelerating expansion driven by dark energy acts like a current flowing through the pond, carrying the ripples of distant events away from us faster than they can approach. This is the great cosmic dissociation. As space stretches, the light cones of distant galaxies are progressively tilted away from our own. Their now and our now are slowly becoming disconnected, their events receding beyond the horizon of our possible knowledge. The shared timeline of the universe is fracturing. We are not just losing sight of other galaxies, we are losing causal contact with them. The universe is breaking apart into isolated pockets of reality, regions that can no longer communicate, share energy, or influence one another in any way. The concept of a unified cosmic present is an illusion born from our brief moment in a relatively connected era. In the far future, the notion of a single universe with a common history will no longer hold true, replaced by countless isolated islands of causality, each with its own separate and unknowable story. A civilization born into that deep cosmic night would face a mystery of unimaginable scale. Their entire reality would be a single, quiet galaxy adrift in an ocean of blackness, with no direct evidence of a larger cosmos or a fiery beginning. To them, the existence of a prior age of light would be a radical, almost heretical idea, a legend with no visible proof. Uncovering that lost history would require a form of cosmic archaeology, piecing together a narrative from clues nearly erased by time. The first and most subtle evidence might be written in the very matter that surrounds them. Within the cold, ancient stars of their galaxy, they could perform a kind of stellar study, measuring the precise abundances of elements. They would find a puzzle. Their galaxy would be composed primarily of hydrogen and helium, the primordial elements from the universe's birth. But mixed within, they would also detect traces of heavier atoms like carbon, oxygen, and iron. These elements cannot be forged in the first moments of the universe or within the cool, stable stars of their own era. Their presence is a fossil record of a more dynamic past. They are the legacy of massive, short-lived stars that lived and faded in spectacular events billions of years earlier, enriching the galactic gas with the seeds of complex chemistry. This unique elemental signature would be a quiet testament to a stellar epoch they could never witness directly. An even more subtle clue might linger in the depths of space itself. As the last supermassive black holes finally complete their long transition, they would not fade silently. In their final instantaneous flash, they would release a burst of ultra-high energy particles and radiation. These final bursts would be incredibly rare and faint, but over quadrillions of years, a few of these high-energy messengers might traverse the void. A far-future scientist with an exquisitely sensitive detector might occasionally register an unusual particle with energy far beyond anything produced in their contemporary universe. Such an event would be a monumental discovery, a direct signal from a long-vanished cosmic giant, proving that structures of immense power once existed. The cosmic microwave background, which tells us so much about the universe's origins, would be completely undetectable, its photons stretched into wavelengths larger than the observable universe. However, its ancient influence might still be faintly imprinted on the large-scale motion of the oldest stars, a subtle gravitational echo of the primordial density variations that seeded all future structure. For this future civilization, cosmology would not be a science of observation, but one of careful deduction. They would be like researchers sifting through the dust of a single, symbolic place, trying to reconstruct the history of an entire world from a handful of scattered artifacts. Each piece of evidence, from the chemistry of a star to the rare impact of a primordial particle, would be a fragment of a larger story. Their greatest challenge would be believing the story those fragments tell, a tale of a brilliant, expansive, and vibrant universe that had long since faded into an unreachable past, a cosmic memory existing only in the subtle traces they worked so hard to understand. This contemplation of a future without memory leads to a profound question of our own responsibility. As the only known species capable of understanding this cosmic story, we hold a unique and weighty role. We are not just observers of the universe, we are its conscious archivists. The vibrant history of cosmic dawn, the age of brilliant galaxies, and the very laws of physics as we know them could be entirely lost to the deep time that follows. This raises a powerful ethical consideration, a duty to preserve a record of this fleeting era of light for any intelligence that might emerge in the far future. The challenge is monumental. How do you create a message that can survive for trillions of years, enduring the slow fade of stars and the gradual evolution of matter itself? One speculative idea involves using the most stable objects in the universe as our library. We could inscribe plaques on the surfaces of neutron stars, those incredibly dense stellar remnants whose crystalline crusts might persist for unimaginable eons. Another, even more ambitious concept is to encode information in the very fabric of space-time, perhaps by influencing gravitational waves or the cosmic microwave background itself, leaving a permanent imprint on the universe's fundamental structure. This would not be a message in a bottle tossed into an ocean, but a message woven into the ocean's very currents. The motivation behind such a project transcends mere curiosity. It is an act of cosmic stewardship, a final gesture of honor for a universe that once teemed with light and structure. We would be ensuring that the story of existence, from its fiery birth to its long, slow quiet, is not entirely forgotten. Even if the actors are gone, the narrative of their brief, brilliant performance would remain. This ethical imperative redefines our place in the cosmos. We are not just temporary inhabitants of a small world, but potential guardians of a universal legacy, tasked with the solemn duty of ensuring that the memory of all that was does not vanish without a trace into the silent night. Our own sense of beauty is deeply connected to the vibrant and ever-changing world we call home. We are moved by a brilliant sunset, the delicate form of a snowflake, or the grand spiral of a galaxy, all born from light, energy, and constant motion. But what becomes of beauty itself when the universe completes its long journey into a state of near total stillness and darkness? In this final, quiet age, the qualities we link with beauty would have no stage upon which to appear. There would be no color, no contrast, no dramatic change. A future form of awareness emerging from and suited to this profound quiet would likely cultivate a completely different aesthetic, one grounded in the core truths of its surroundings. For such a mind, beauty might not be found in a spectacular event, but in the uncovering of a perfect, timeless mathematical truth. It could be sensed in the complete symmetry of a cold, empty space, or in the graceful, predictable fading of a single particle over an immense age. The complex equations mapping the universe's steady, uniform condition could be their art, their poetry. The slow, certain movement toward maximum entropy, which to us suggests a conclusion, might be viewed by them as a condition of ultimate and peaceful balance, a form of cosmic harmony. This line of thinking uncovers a deep truth about beauty itself. It is not an absolute quality written into the universe, but a relationship between a conscious mind and its world. Our aesthetic is a product of the stelliferous era, a reflection of a cosmos filled with temporary, energetic forms. A consciousness born into the deep cold would have a sensory and intellectual framework shaped by permanence, silence, and simplicity. Their great work might be the proof of a theorem that shows the universe's final, unchangeable state. Their most profound moment could be the detection of a gravitational wave from a source that faded an eon ago, a single, soft ripple in space-time telling a tale of a past they can barely imagine. This change in viewpoint questions our deepest beliefs about what makes existence meaningful or worthwhile. It implies that even in the total absence of all we find beautiful, the possibility for a different kind of wonder persists, shaped in the bond between mind and cosmos, no matter how dark or still that cosmos may one day be. Even in the profound darkness of the degenerate era, the cosmos is not yet completely still. The last sources of light are not the steady glow of stars, but the isolated, random flickers of stellar remnants in their final act. These events are the ultimate cosmic afterglow, separated by intervals of time so vast they make the current age of the universe seem like a single breath. Among the coldest and darkest of these remnants are the brown dwarfs, objects too small to ever sustain the full fire of nuclear fusion. Drifting through the eternal night, these failed stars are so faint they are little more than embers. Yet, in the deep quiet, a rare gravitational dance can occur. Two of these dark, cold objects might slowly spiral toward one another over eons, drawn together by their weak mutual pull. If they merge, their combined mass could, for a fleeting moment, reach the critical threshold needed to ignite a brief, faint red star. This would be no brilliant sun, but a temporary flare in the endless dark, a last, lonely beacon shining for a mere cosmic instant before fading once more into the cold. An even more final and speculative flicker awaits the black dwarfs themselves. These cold, crystalline spheres, the end state of stars like our Sun, are not entirely inert. Deep within their incredible density, a strange and slow process could theoretically occur. The immense pressure might, after timescales beyond comprehension, force atomic nuclei together in what are known as pycnonuclear reactions. This would not be the sustained fusion of a living star, but a sudden, silent flash, a release of energy as the star's own carbon and oxygen atoms are forced to combine. Imagine a single, perfect diamond the size of a planet, sitting in absolute darkness for a time longer than all of human history. Then, deep inside its core, a silent, invisible transformation occurs, producing a single, final pulse of light. This event would be so rare that only a handful might occur across an entire galaxy over a span of trillions upon trillions of years. Each one is a final, fleeting echo of the universe's once brilliant past, a last whisper of stellar process before the final, unbroken silence falls. In a cosmos where nothing new is born, these random, isolated flashes are the final punctuation marks in the story of light, brief reminders of the vibrant era that came before the long, dark night. This grand cosmic narrative, from a brilliant dawn to a deep and distant night, frames our existence with startling clarity. Our journey through the fate of light reveals a universe not of static permanence, but of continuous, breathtaking transition. The predicted quiet is not a story of loss, but a powerful reminder of the dynamic reality we are part of, a cosmos that is alive with change even in its most still moments. Our brief, brilliant epoch of starlight is a singularly precious chapter in this immense story. We have the profound privilege to exist now, to witness the splendor of galaxies, to feel the warmth of a star, and to ask the great questions about where it all began and where it is all going. This knowledge does not diminish our moment, it illuminates it. Let this understanding of an eventual quiet inspire a deeper appreciation for the fragile, beautiful now. If this exploration of cosmic transitions has expanded your perspective, we would be honored to hear your thoughts in the comments and to have you join us for more journeys to the edges of understanding.